Hello ladies. Today in this video I'm going to be going over quiz 6 with you. I know that you asked for this because you were having issues with it while you were taking the quiz in class, so here we are. We're going to go over it now, okay? Let me make sure my pen works. Yep, okay. So the first question asks, and remember these questions are not in the same order as they are in your quiz because Blackboard automatically randomizes it. Anyway, the first question asks, it says that an aqueous solution of a compound did not form precipitates with bromide, chloride, iodide, sulfate, carbonate, phosphate, hydroxide, or sulfide, right? So what that means then is that when you see it did not form precipitates, that means that it was soluble in water. Okay? And then this highly water-soluble compound produced a foul-smelling H2S gas when it was acidified. What is the name of this compound? Well, this one's pretty easy because all you really have to do is look at the chart, right? So you're looking for, you already know that it makes you already know that it has to have sulfur in it, number one, right here, because it makes H2S gas, right? It has to have sulfur in it. And so that's the first thing that you can see. And then if you look at the rest of these answers here, carbonate there doesn't have sulfur, nitrate doesn't have sulfur, bromine doesn't have sulfur, nitrate doesn't have a sulfur, right? The only one that has a sulfur is ammonium sulfide. So that was your first clue that it's probably that answer. But the legit way of doing this, the real way of doing this, is to go to your chart, right? And for this one here, we're looking at our chart right here. And you can see right here the sulfide ion, right there, S2 minus right there, is in the insoluble chart, but its exception is ammonia, which is right there, NH4, right? So if you go back to our quiz right here, this is ammonium sulfide, right? So not only, since there's the the only compound in the list of answers that has sulfur is ammonium sulfide, right? You can even look up ammonium sulfide to make sure it actually is soluble in water, right? And again, you do that by going over to the chart, right? You find ammonia and you find sulfide. In this case, it will be sulfide, right? And here's sulfide right here, the insolubles, right? So that gives you that kind of thinks you think that it's actually insoluble, right? But then if you look at the exceptions, one of the exceptions is actually ammonium right there, right? Ammonium sulfide. So ammonium sulfide right there, right? I don't know if you can see that or not. So let me mark that so that you can actually see it. Let's close this part here and turn on the pen. There we go. So yeah, we look up sulfide right there. And then we have ammonium right here, right, which matches, and so it says that compounds containing sulfide are insoluble, but if they have ammonium in it, they are soluble. So that's ammonium sulfide. You put those two together, and then the answer here that's soluble is ammonium sulfide. All right, so the next question, I know this is an acid-base reaction, but really what it is that, and I know I didn't cover neutralization reactions in class yet, but the question isn't really about a neutralization reaction. It's about knowing how to balance a chemical equation, right? And so your chemical equation always starts out with a reactant, which is H2SO4, and the other reactant is KAOH, right? So you start out by writing H2SO4, right? Don't forget the AQs. Plus, that's sulfuric acid, by the way, plus potassium hydroxide, again an AQ, right? And then that makes some kind of product. And remember, the only reason why it says neutralization right here is to remind you that neutralization reactions always end with salt and water, right? And so the salt here will be potassium sulfate, which I think I forgot to raise potassium group 2. Yeah, just while we have our periodic table. No, potassium's group 1 right there. Okay, so since potassium is group 1, and it's going to be potassium sulfate. Sulfate is a group, has a as a polyatomic ion has a -2 charge, so you need 2 potassiums for every sulfate, and then that makes and also ends up having water there, right? So now this is not a balanced chemical equation, because you notice over here there are 2 potassiums, and there's over here there are 2 potassiums, and over here there's only 1 potassium, so you don't have a balanced chemical equation there. So this is the answer to the question right here, right? This is how you figure out, this is how you answer the question. You have to figure out what the balanced chemical equation is. So remember that the only thing you can do to balance a chemical equation is to put coefficients in. Remember, changing a subscript will change the molecule itself, but putting in a coefficient will only change the number of moles of the molecule that's present. Right? So I would probably start out by saying, well, if I look over here, I have 3 H's over here, right? 1, 2, and then 3, and then I have only 2 over here, right? So one easy thing you can do here is that you also notice that there's 2 potassiums, only 1 potassium here, right? So if I start out by saying, oh, well, I need 2 potassiums on both sides, I can put a 2 here, like that, and now it's 2 potassiums, and I have 2 potassiums on both sides. But then the other interesting thing here too is that it makes it so that now I have 2 H's with the potassium, because 2 times that 1 H there is 2 H's. And so now there's 2 H's here on this side, and then there's 2 H's here on this side. All right? That's a total of 4 H's, okay? But over here, on the product side over here, I still only have 2 H's. I don't have 4 H's. So what do? Well, easy. I just added 2 in front of there, in front of the water, and now I have 4 H's, right? 4 times 2. 2 times 2 is 4, so that's 4 H's. That also makes me have 2 oxygens as well. And check that out. I also have 2 oxygens over here. So the answer then is H2SO4, sulfuric acid, plus 2 KOHs, potassium hydroxide. So it will make 1 potassium sulfate and 2 waters. And so that answer is right here, the one that's been already check marked right there. Right? So while this is technically a neutralization reaction, it's not asking you for anything but how to balance this chemical equation. Next, right, another question about doing chemical reactions, balancing chemical equations. Again, right, we have 2 molecules here that we have to figure out what the balanced chemical equation is for. Right? So aqueous acetic acid and potassium hydroxide. We saw potassium hydroxide earlier, just in the previous question. That's KOH. That's the base, right? And then sulfuric acid, which is, not sulfuric acid, acetic acid, right? Which is HC2H3O2, okay? And then, of course, just like any other acid-base or neutralization reaction, we always end up with a salt and water. And so the salt here will be potassium acetate plus water. All right, potassium acetate plus water, okay? All right, so as we look at this equation and we start counting things up, let's see here. We have one potassium acetate ion there, and we have one acetate ion there. That's good. Then we have 1 potassium there and 1 potassium here. Then we have 1 hydrogen here, 1 hydrogen here, and then we have 2 hydrogens here, and then we have 1 oxygen there and 1 oxygen there. So luckily for us, this particular equation is already balanced, right? We don't have to add any coefficients, and so that is borne out in answer D right there. Okay. Next question. What is the net ionic equation for the reaction between sulfuric acid and aqueous sodium hydroxide? Right? Well, if you remember, whenever you do a net ionic equation, it gets rid of all the ions, right, that are aqueous, the ones that are dissolved in water, right? It gets rid of all those ions and leaves only behind things that were not dissolved in water, right? And in this case, it might actually even be water itself. Okay, and so if you look at all of these answers have AQs in them, right? And if they have AQs in them, that means that these are all spectator ions, right? And so none of these answers can be correct. Remember, the net ionic equation only has in it a solid, or liquid, right, or even a gas maybe, but it's not going to be something that's going to be that's going to have been dissolved in water, right, an aqueous phase. And so the only one here, the only answer here that doesn't have an aqueous phase in it as a product is that one right there. Because remember, once again, a net ionic equation, you actually cancel out all the the ions that are aqueous, right? Leaving behind only the ions that make the one product that's not going to be aqueous anymore, right? And so the only answer here that actually has a product that's not aqueous is C right there. You see that? Over here we have for B we have aqueous sulfate, aqueous sodium. Over here we have aqueous sodium. So none of those are it because they all have aqueous in their products, right? Here we have aqueous for D in their products too. We do have a water here, but we still have an aqueous sulfate right there, so that can't be the answer. The only one that makes any sense is the water, because the water does not have an AQ. Remember, when I say aqueous, I'm talking about having an AQ right in the behind the element name, the atom name, right? AQ means dissolved in water. Right? And so when you're doing the net ionic equation one more time, you're always going to have two ions, right, on the left side of the arrow, or the reactant side of the arrow, and those two ions will combine, and so that will be the aqueous stuff, and those two aqueous ions will combine to make something that's not aqueous technically, right, not dissolved in water, right? And here we go, the only two ions right here, H plus hydroxide minus, making something that's not AQ, because we have an L right there for liquid, is water. So that's definitely going to be number 4. Or it's not number 4, the answer is number 4 is C. Okay, number 5 says, which combination will produce a precipitate? This is easy because all you have to do is look at the chart, right? And you do what I call the double replacement reaction, or the Swinger's reaction, right? So if you have here potassium hydroxide and magnesium nitrate, right? They'll switch partners, and you'll get potassium nitrate potassium nitrate plus magnesium oxide. Right, magnesium oxide. Okay, and the thing about it is that you don't even have to balance these. You just need to check to see if these guys are soluble right here, right? And so if we look and see on our chart, we have nitrate compounds. So just off the top of my head, I know that nitrates are always soluble. So that's not going to be the thing that's actually soluble, right? Insoluble, or makes it precipitate. Because remember, precipitate is something that's insoluble. But I'm not sure about magnesium and hydroxide, so we'll look that up in the chart. And so over here on the chart, we have hydroxides right here at the bottom, right? And turns out that all hydroxide compounds are insoluble, except for ones with ammonia, right? Ammonia, calcium, strontium, and barium, right? Magnesium is not listed in that chart, and so then we know that we didn't even have to check all the other ones because the magnesium hydroxide we already know is insoluble, and that's going to be the precipitate. Insoluble means precipitate. Precipitate. Almost didn't know how to spell that right there. Right? Another one of these that's pretty easy, right? Which of the following is an insoluble compound and water? Again, just check all these things, check all these ions, right? And let's see, we'll just go and do the first one, right? The first one, that one's ammonia and carbonate. So let's look at our chart. Ammonia and carbonate. So here's ammonia. So here's carbonate right here. All right. There's carbonate, and it's in the insoluble list. But remember, right there is an exception. Ammonium carbonate is actually soluble. So the answer can't be that. Next one is nitrogen sulfide. So let's look up nitrogen sulfide. Sulfide's up here, right? And nitrogen sulfide's up here. And notice that right here it says that nitrogen sulfide, again, it's in the insoluble compound list, but it says in the exceptions that all sulfide compounds that have an alkali metal, which is the group 1 metals, right? Group 1 metals are soluble. And so if we look over here, back to this, sodium is a group 1 metal with sulfide, so it's soluble. It can't be that one. And then we have magnesium phosphate, which is checked as the answer here, so but let's just make sure it's right. Okay, magnesium phosphate, notice right here, phosphate is in the insoluble group. That's good so far. But it doesn't say that the alkali earth metals make phosphate soluble. It's just the alkali metals. Remember, because alkali earth metals, alkaline earth metals are group 2A, right? They're group 2A, not group 1A. And so go back over here and we see that magnesium here is a alkaline earth metal, group 2A, with a phosphate, makes it insoluble. So that's the answer. You can stop right there. You don't have to check all the other ones. Next question. It says, which of the following compounds is insoluble? Again, all you have to do is check the chart. We already know that magnesium right here, right, is insoluble from the previous question with most things, right? But we have the chromate ion right here. I think is that chromate? I don't know. C2O4 oxalate maybe. I can't remember what that is. It's either oxalate or chromate, but that doesn't matter, right? And we can go back over here, and I just want you to see here that. Let's see here. None of the exceptions again, right? None of the exceptions actually contain the group 2A or the alkaline earth metals. So if you go back to this one right here, right, you know that all chloride ions are soluble, right? Because on the chart right here it says chloride is soluble, okay? And then you know that all, let's see here. Is acetate listed? Yes. Acetate's right here, right? It's also all acetate compounds are soluble, right? And so that's acetate right there. Can't be that one or that one because we're still looking for an insoluble. Oh, we know that nitrate compounds are all soluble too, so it can't be that one. And sulfate compounds, let's just make sure. Sulfate compounds right there, right? All soluble except for strontium, barium, mercury, and lead. And so we had potassium sulfate, so that's definitely soluble. So the answer is this, right? So again, all you had to do is look at the chart. All right, so the next couple of questions are just molar ratios of stoichiometry, which are super simple. We did this a few times in class already, but we'll do it again here. So you have here lithium nitride. You have 1.75 moles of it. Assume that you had excess nitrogen in this reaction, right? So how many moles of lithium nitrate can be formed, right? Well, pretty simple here. I would start out by saying that we have I would start by saying this right here. Okay, we have 1.7 moles of lithium. So 1.75 moles of lithium. Start up my stoichiometry or dimensional analysis. For every 1 mole of lithium, how many moles are there? Of lithium nitride? Right? It's 2 moles. I actually did this wrong. I read the number wrong. Look right here. See, it's actually 6 moles. For every 6 moles of lithium, we get 2 moles of lithium nitride. Right? Oops. And I'm writing this all wrong. Li3N. There we go. And that should give us the number of moles of lithium nitride. Okay? As simple as that. So all you have to do is multiply 1.75 times 2 and divided by 6. Right? And again, I got the 1.75 from here in the question. I got the 2 moles of lithium nitride from here in the balanced chemical equation. I got the 6 moles of lithium right here from the balanced chemical equation, right? And let me pull out a calculator real quick. Oh, you know what I forgot to do actually? I forgot to move it to grams. So let's erase a little bit here. I forgot to also convert to grams. How do we convert to grams? I just keep on going with this. Like that, right? And then for every 1 mole of lithium nitride, oh my god, I can't believe I messed it up. Keep on writing the formula wrong. Oops. I forgot I could erase. I could have erased all these mistakes I made right here. It's okay though. There we go, lithium nitride. And now I got to put the molecular weight of lithium nitride, which is easy because I can go back to my periodic table, which is right here. And lithium's molecular weight is right there. Okay. And then nitrogen's molecular weight is right here. Right? So I had 3 lithiums, so that's 3 times the molecular weight of lithium, which is 6.941. 6.941, right? And then I'm going to add that to the molecular weight of nitrogen, which is 14.007. So the molecular weight came out to be, for Li3N, came out to be 34.83 grams per mole. So I'll go back to my calculation over here, put in 34.83 grams, and now that should get me the answer. So now what I do is I multiply the 1.75 times 2 times the 34.83, divide all by 6. So 1.75 times 2 times 34.83, and then divide all that by 6, and I get the answer to be 20.13175 grams of lithium nitride, right? And so we have 3, I think. Yeah, we have 3 sig figs. And so to make it 3 sig figs, I round down right there. So the answer is 20.3 grams of lithium nitride. And let's see if there's an answer for that. Oh, and it's right there. See? Just regular old stoichiometry. Alright, here's another one that's balanced chemical equation again. Okay, so it's the equation of ammonium acetate with aluminum acetate with ammonium phosphate. So this is one of those double replacement reactions or swingers reactions, right, where they just switch partners. All you got to keep in mind here is the charges for each of the ions. So remember that, let me give myself a little room up here. Remember the acetate has a -1 charge. Aluminum has a +3 charge. Okay. And then ammonium right here has a +1 charge, and phosphate here has a -3 charge, right? So since aluminum and phosphate have the same charge, but just opposite of each other, we know that they'll go to 1-to-1 with each other, right? They'll go 1-to-1 with each other. And then since acetate and ammonium have 1-to-1, have the same charge but just opposite each other, they also go 1-to-1 each other, right? So your products from this are going to be aluminum phosphate, right? And oops, that's phosphite. Let me fix that. Oops. Okay. Phosphate plus plus ammonium and H4 acetate, which is C2H. I always forget the formula for acetate. Oh, it's over here. Oh, it's actually right there. There's C2H3O2. Right? So that's pretty easy. So if we look at all these reactions and their products, right, they all are going to have the right one, I think. See, aluminum phosphate, ammonium acetate, aluminum phosphate, ammonium acetate. So again, these balanced chemical equation things are super easy, because you can either go through and balance it yourself and see what matches, or you can go through and just make sure that everything has the same number of atoms on both sides, right? So let's look at the first one here. There's 1 aluminum on the reactant side here, and there's 1 aluminum on the product side right there. There's one acetate on the there's 3 acetates right here. Okay, there's 3 acetates right here on the product of the reactant side, and there's also 3 acetates over here, right, on the product side, because there's a 3 in coefficient right there. And then there's 3 ammonias right here, also 3 ammonias on the product side, right, because of the coefficient. Then 1 phosphate there, 1 phosphate there. So you just go through and make sure they have the same number of atoms on each side, right, of the equation, of the chemical equation, each side of the arrow, and you can do process of elimination that way. And since you found that the first one is, all nice and mass is conserved on both sides of the equation, then that's the right one. You don't have to even go check the other ones. All right. So, I just want to remind you that, you really shouldn't be thinking too hard about these questions. These questions are really easy if you just don't think about them too hard. Make them out to be harder than they actually are. All right, so here we go. Another stoichiometry question. According to the following reaction, how many grams of sulfur are formed when 37.4 grams of water, right, are formed? Okay, so there's the water on that side, and there's the sulfur. Again, this is just regular old stoichiometry. Since the water grams is the only thing you have, you're going to have to start with that. So 37.4. You know what? I need to start over. I need more room. I'm going to start over here. No, dang it. I'm trying to erase. There you go. Erasing on a PDF isn't as fast as erasing on a PowerPoint. Okay, so since the only number you have here is the water, we'll start with that, right? And of course, my pen mark blocked it, and I can't read what it says. There we go. Okay. So 37.4 grams right there, okay? Okay, so we start out with saying 37.4 grams of water. Okay, for every 1 mole of water, remember we have 18 grams of water. Where did I get the 18 from? I just added up the weights of hydrogen plus a hydrogen plus an oxygen. Okay, and then we go back to our chemical equation right here. Our balanced chemical equation, it says for every 2 moles of water, I have 3 moles of sulfur. That's what it's looking for. Okay, and then I want to be able to convert the moles of sulfur into grams of sulfur. So for every 1 mole of sulfur, what is the we put in the molecular weight of sulfur, which I can't remember what it is, so we'll look it up on the chart. Right here, sulfur, there you are. Sulfur's right there. 32.00, so 32.06. So 32.066 grams of sulfur. And so that should give me grams of sulfur at the end, which is what the question was asking for. So I can cross out grams of water with grams of water, moles of water with moles of water, moles of sulfur with moles of sulfur, and so all I'm left with is here, which is grams of sulfur, which is what the question was asking for, right? So all I have to do now is multiply 37.4 times 1 times 3 times 32.066, divide all that by whatever 18 times 2 is, right? So let's do that real quick. 37.4 times 1 times 3 times the molecular weight of sulfur, which is 32.066. We get a number. We divide all that by 18 times 2, or 36 times 2. 18 times 2 is 36. So I got, my answer was 99.93033, right? And so I'm repeating numbers, right? Again, it's we could look here and we see that the number of significant figures we have is 3 sig figs, right? 3 sig figs. So this has to be rounded off to 3 sig figs, and so that's going to be the answer right there, 9.99. Look at the answer choices. Definitely not 6.66. That's wrong. Can't be 14. That's off. 56 wrong. 44 off. The closest one is this one, 99.8 grams of sulfur, right? So that could have just been a very, very negligible rounding error that I got 99.9, and the answer says 99.8. They're essentially the same. Well, that's all of quiz 6. I hope you were able to hang in there with me and learn how to work these problems. There will be some repeats of these types of problems on the exam on Tuesday, so study them hard. And if you have any questions, DM me on the team. So I'll be there. I'll be on my teams all weekend, of course. And just again, one last time, don't think about these questions too hard. If you think about them too hard, that's when you start second guessing yourself. You're not sure how to work these problems, but everything you need is there in front of you. Okay. Thank you, ladies. I'll see you on Monday.